Hello, everyone. This is Chemical Bonds Made Simple with Miss Rodriguez, and today we're going over everything you need to know about the chemical bonding unit in high school chemistry. Today we're covering types of bonds, ionic nomenclature and Lewis structures, covalent nomenclature and Lewis structures, and VSEPR theory. Starting with our octet rule, which is the reason why we have bonds to begin with. The octet rule states that all elements want to have 8 valence electrons in order to become stable. The only exception to this rule is hydrogen and helium, which only require 2 valence electrons. There are 3 types of chemical bonds: metallic, ionic, and covalent. Covalent bonds can be further broken down between polar and nonpolar. Metallic bonds are between metal and another metal. They have a sea of delocalized electrons, and they produce alloys. Delocalized means that the electrons do not have to stay by their nucleus. They're free to move around. And an alloy is a solid solution of 2 or more metals combined. The electronegativity difference between the 2 elements are going to be small, and the properties of a metallic compound are high melting and boiling points. They're good conductors of electricity and heat, and they're shiny. Examples of a metallic compound are steel, brass, sterling silver, and 14-karat gold. Ionic bonds are between a metal and a nonmetal. In an ionic bond, the electrons are transferred, forming an anion and a cation. The anion is the one that gains the electron. The cation is the one that loses an electron. The electronegativity difference between the two are going to be large, so they're going to be more than 1.7. The properties of an ionic compound are high melting and boiling points, solid at room temperature, they dissolve in water, and they conduct electricity. And the solids are going to be brittle crystalline solids. Examples are going to be things like salt and lye. Covalent bonds are between a nonmetal and another nonmetal, or a nonmetal and a metalloid. In a covalent bond, the electrons are going to be shared. Every element in a covalent bond is going to end up with 8 electrons. But again, that's with the exception of hydrogen, which only needs 2. A diatomic molecule is a covalent bond between 2 of the same atoms. So for example, H2. Covalent bonds can be broken up between nonpolar and polar. Nonpolar means that there are equal sharing of the electrons. Polar means there are unequal sharing of electrons. That means one of the elements is holding onto that electron a little bit closer to its nucleus. The electronegativity difference is going to depend on whether it's polar or nonpolar. Nonpolar have very, very small electronegativity differences, less than 0.5, and polar are going to be between 0.5 and 1.7. The properties of a covalent compound are lower melting and boiling points than ionic compounds. They could be solid, liquid, or gas at room temperature. They do not dissolve in water, and they do not conduct electricity. Examples of covalent compounds are carbon dioxide and water. Now let's go over ionic nomenclature and Lewis structures. First, familiarize yourself with the transition metals. So this is the transition metal family, the middle section and the bottom section of the periodic table. The reason we have to be aware of the transition metals is because they have multiple possible charges, with the exception of the following elements. Zn always has a +2 charge, Cd +2, Ag is +1, Pd is +4, U is +6, and V is +5. But every other metal in the transition metal family have multiple possible charges that they could have. We also have to know the polyatomic ions, and those are groups of atoms with a net charge. This list can be found on the back of the star periodic table if you use it for reference. There are 3 easy steps to naming ionic compound. The first step is you identify which of the elements is your metal and which one is your nonmetal. The name for the metal stays the same, so you don't change it from the periodic table. For the nonmetal, the ending is dropped and replaced with "ide." For example, in NaCl, Na is our metal, Cl is our nonmetal. Na on the periodic table is sodium, Cl on the periodic table is chlorine. Sodium stays sodium, chlorine becomes chloride. The exceptions are when you have a polyatomic ion. The polyatomic ion, you do not drop the end. It stays the same as the name you see on the list. And transition metals. Transition metals have multiple possible charges. So in order to let people know what charge the transition metal has, you have to use Roman numerals to show the charge. When you write ionic formulas, it's only 2 steps. You figure out each atom's charge, and then you have to make the overall charge equal to 0 by changing the subscripts. You determine the atom's charge by looking at their number of valence electrons. So how many valence electrons does that element want to gain or lose in order to become stable? For example, Na has 1 valence electron. In order to become stable, it's going to lose that electron, so it has a +1 charge. Cl has 7 valence electrons. It wants to gain an electron in order to complete its octet, so it's going to have a -1 charge. Na plus 1, Cl minus 1, they already balance out to 0, so all you need is one of each. So the formula would be NaCl. If you have a polyatomic ion and you need more than one of them to balance out your formula, make sure to put it in parentheses. It's easy to do the ionic Lewis structure if you already know the formula. First, you figure out the charge of each of your atoms. So K2O, K has 1 valence electron. It wants to get rid of that electron, so +1. O has 6 valence electrons. It needs 2 more to complete its octet, so -2. You put brackets around all of your atoms. So brackets around K, brackets around O. Put the charges on the outside of the bracket on that top right area. Make sure you put how many of each atom you have at the front, and you draw your 8 valence electrons around your anion to show that it has a full outer shell. Covalent nomenclature and Lewis structure looks a little bit different compared to ionic. There are 3 steps to naming a covalent compound. First, you figure out how many atoms of each element you have. Then you give prefixes to both of your elements, and that prefix tells you the number of atoms. The only exception is when there's only one of your first nonmetal, then you don't give it a prefix. The second nonmetal always has a prefix, and just like with ionic, you drop the end and replace it with "-ine". The prefixes are listed here. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. If we look at CH4 and we follow our steps, so step 1, C has no number next to it. That means there's only 1 carbon. H has a 4 next to it, so that means there are 4 hydrogens. Let's assign our prefixes. Normally, 1 would be mono, but since carbon is the first element, it doesn't get a prefix. The prefix for 4 is tetra, so we're going to put tetra with our hydrogen. We drop the N, replace with "-ine, and you get our covalent compound name, which is carbon tetrahydride. When writing covalent formulas, if you already know the name, it makes it very simple if you know your prefixes. All you have to do is write the chemical symbols for the elements in your compound, and then you figure out the number of atoms by looking at the prefixes. For example, in carbon tetrahydride, the carbon had no prefix, so we know that there's only 1. The tetra in front of the hydride, tetra means 4. So our formula is CH4. Covalent Lewis structures need to show how the electrons are being shared between the elements involved. First, we need to calculate how many electrons are in the compound. Then we form bonds between our atoms so that each atom has a full valence shell. For the majority of atoms, this is going to be 8 valence electrons, but only 2 if it's hydrogen specifically. We replace the dots with lines to represent that the electrons are being shared, and we make sure to use all of the electrons that are in the compounds. For example, in CH4, we have 1 carbon and 4 hydrogens. Never put hydrogen in the center of your Lewis structure because hydrogen can only make 1 bond. Carbon has 4 unpaired electrons. Hydrogen has 1 unpaired electron. Because they are unpaired, we can bond these unpaired electrons, and once all of the bonds are drawn, we can see that all of the elements have fulfilled their octet. So there are now 8 valence electrons that carbon has access to, and for each of the hydrogens, they now have 2 valence electrons that they have access to. So all of the elements in this compound have fulfilled their octet. When we look at a covalent Lewis structure in a 3D format, we are able to name its molecular geometry. This is called the VSEPR theory. According to VSEPR theory, in covalent compounds, the shape is determined by the repulsion between electron pairs in the valence shell. Molecular geometry is just another way to say the shape of the compound when VSEPR is in effect. Polar covalent compounds are going to have unequal sharing of their electrons, meaning that they have at least 1 lone pair. And nonpolar covalent compounds have equal sharing of their electrons, meaning that there are no lone pairs. And when we're talking about polar and nonpolar and lone pairs, we're only talking about that middle atom. So whatever element you have in the middle of your compound. There are 5 VSEPR shapes that you need to know for high school chemistry, and in order to figure out the molecular geometry, you have to draw the Lewis structure first. And this is so you can see if there are lone pairs on the central atom, which determines the shape or the molecular geometry of your compound. The first of our VSEPR shapes is linear, and linear is when you have 2 bonded pairs and no lone pairs. So if we look at carbon in the center, it has 1 bond to the oxygen on the left and a second bond to the oxygen on the right, and no dots, so no lone pairs in the center. Bent is when you have 2 bonded pairs and either 1 lone pair or 2 lone pairs. The oxygen in the center is bonded to the hydrogen on the left and is bonded to the hydrogen on the right. It has a lone pair on top and a lone pair at the bottom. Notice that in this example, there's only single bonds, while in the previous example, there were double bonds. It does not matter if it's a single bond, double bond, or triple bond, as long as the same elements are bonded, then it only counts as 1 bond for molecular geometry. If you have 3 bonded pairs, then you either have trigonal planar or trigonal pyramidal. Trigonal planar is when you have 3 bonded pairs and no lone pairs. It's easy to identify trigonal planar because it's always going to be boron in the center. That's because boron is special. Unlike most elements which need 8 valence electrons, boron is perfectly happy with 6. So boron is stable with 6 valence electrons, so it can form the trigonal planar shape. Trigonal pyramidal is when you have 3 bonded pairs and 1 lone pair. For example, we have nitrogen in the middle, which has 5 valence electrons, so it can form 3 bonds, one with the H on the left, one with the H on the bottom, and one with H to the right, with the remaining lone pair at the top. Tetrahedral is the final VSEPR shape, and that's when you have 4 bonded pairs and no lone pairs. So if we look at our image, we have carbon in the middle, surrounded by 4 hydrogens, each bonded with a single bond, and no lone pairs on the central atom, so no dots. All right, that is everything you need to know for chemical bonding in high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If this video was helpful, make sure you hit the like button and subscribe so you don't miss any of my future chemistry content. If you're a chemistry teacher and you want access to this exact PowerPoint, it's on my TPT store at Chemistry Made Simple. as well as worksheets, labs, and activities that align with this unit of chemistry, as well as other resources that cover the whole year of chemistry. I hope you have a great day. Bye!